Okay, so we're going to be looking at finding the area of regular polygons. And the figure we're starting with first is a pentagon with 5 sides. It could apply to other regular polygons as well, but that's the one we're starting with. And if we kind of break this down, remember, if we have our center of this pentagon, we can extend out radii from the center to each vertex. Notice the radii, the number that we have, just like we talked about before, matches the number of sides. There's 5 radii, 5 sides. And then also, we have 5 triangles, okay? So we can think about finding the area of the pentagon this way. If I find the area of one triangle and multiply that by the number of triangles that we have, in this case 5, that would give me the area of the pentagon, okay? So that's actually kind of where this idea starts, is that if I take the number of triangles, in this case 5, and multiply that by the area of one triangle, which would be 1/2 the base times the height, that would give me the total area of our pentagon, okay? But notice the number of triangles matches the number of sides. We have 5 triangles and 5 sides. So instead of saying the number of triangles, we could just say the number of sides, which is still 5, multiplied by 1/2. Well, what's the base of one of these triangles? Well, the base of one of our triangles, let's just look at this guy here. The base of one of our triangles is the side of our pentagon, okay? This guy right here is the base of, let's look at this triangle, okay? So it's the base of this triangle, it's just the side of our pentagon. Now, the height of this triangle is the apothem, okay? So we talked about this before. It extends from our center, and it's the perpendicular segment that meets the side of our figure, okay? So the height here is the apothem, okay? So the area of one of our triangles is 1/2 the base, which is just the side of the pentagon, times the height, which is the apothem, and then we multiply that by the number of the sides, and that would give us the area of this pentagon, okay? So that's what they're saying here, is that we have 1/2 the side length times the apothem is the area of one triangle, times those 5 sides gets us the area of all those triangles, okay? But notice, if I take the number of sides and I multiply it by the side length, because we can multiply in any order, isn't that really the perimeter? Well, yeah, okay? So if I know one of the side lengths is, let's say, 10 centimeters, okay, and I multiply that by 5, that gives me the perimeter. Well, that's what that's saying there, is if I take the number of sides times the side length, that's really the perimeter. So what we end up with is this equation here. Area is 1/2 the perimeter times the apothem, okay? So we can use this equation here, area is 1/2 the perimeter times the apothem, to find the area of a regular polygon, okay? So for instance, let's look at these examples here, okay? We have area is equal to 1/2, and I'm actually going to put A before P, doesn't really matter. The apothem times P, okay? P for perimeter. So if that's the case, we have 1/2. Our apothem is 11 in this figure, from here to here, okay? That's the apothem. So we have 11, and then the perimeter. Well, notice they give us one of the side lengths. This is a pentagon. We have 5 sides. So if I take 16 times 5, that gives me the perimeter all the way around. Well, 16 times 5 is 80. So the perimeter of our pentagon is 80. Now we can find the area, okay? So if we take 1/2 times 11 times 80, okay, multiply that in our calculator, we get 440 centimeters squared. Okay, 440 centimeters squared. Okay, so that's how we're going to be able to find the area of a regular polygon. Okay, and we'll do the other examples in class together. But what if they don't tell you what the apothem is? And in that case, there's actually 3 specific regular polygons we're going to look at that involve special right triangles in which we can find the apothem in order to go through the same process. The area is 1/2 P times A, or A times P, the apothem times the perimeter, okay? And that's what they're talking about in these next examples here. It says, notice, if we look at an equilateral triangle, a square, and a hexagon, okay, there is a pattern from which, if we look at the center from the center and our apothem here, and then the center with our radius, okay, that helps form another side. Notice it forms a triangle here, okay? And specifically, this triangle is going to be a 30, 60, 90, okay? Or we have our radius, our apothem, and then one of the side lengths, okay? And in fact, this is actually half of this side, okay? So if we look at this, this would be the full side. This is only, this piece right here, is only half of that side, okay? But it forms a 30, 60, 90 degree triangle, one of our special right triangles. And then with a square, it also does the same thing. We have the center, apothem, center, radius, then half of that square side, and it forms a 45, 45, 90, okay? And with the hexagon, center, apothem, center, radius, and half of this side forms a 30, 60, 90. It's a different configuration. So with this guy, we had 30 here. With this guy, we have 30 here, okay? But it's still a 30, 60, 90 degree right triangle, okay? Now, what's useful about that is we remember that there's a special relationship between the sides, okay? So if I have a 30, 60, 90 like in this configuration here, we know the short side we can always think of like x. The hypotenuse is always twice x, and the long side is always x times the square root of 3, okay? Then for a 45, 45, 90, the two sides opposite our base angles will always be the same because we have an isosceles right triangle. If we think of this side as x, then its side over here would be x, and the hypotenuse would be x square root of 2, okay? Now, this is also a 30, 60, 90 that it's just, again, it's in a different configuration. It's in, or I should say orientation, but the short side is still going to be x, the long side is still going to be x squared to 3, and then our hypotenuse is going to be twice x, okay? So that's why it's useful there, because notice, then I know how to find the apothem, and then I can use that equation that we looked at earlier. A is equal to 1/2 AP, or PA, doesn't really matter, we can multiply in any order, apothem times the perimeter, okay? So with that in mind, they give us an example here, and they say, given that we have an equilateral triangle with a radius, that's important, a radius is 6 centimeters, we want to determine the area. So what they're saying is if I give you that the radius from the center to one of our vertices is 6, can we determine enough missing information here in order to find the apothem, find the sides, and then therefore find the area? Well, we can, because this is a 30, 60, 90 triangle, okay? So remember, based on what we just saw above there, if we have a 30, 60, 90 triangle, this will be x, the short side, long side is x squared to 3, and then the hypotenuse is twice x. Well, our radius is our 2x. They tell us that that's 6. Well, if this side is double this side, what does x have to be? Well, the x has to be 3. So what they're saying is this guy is 3. Well, notice that's our apothem. That's the height there of this triangle, okay? So our apothem is 3. Well, if this is 3, this makes this 3 square root of 3, okay? 3 square root of 3. So this side here would be 3 square root of 3. But remember, that's half, okay? That's half of the total length here. So then this side of the triangle would also be 3 square root of 3, which means in total, the side length of our triangle, the big triangle here, okay? The side length of our big triangle would be this plus this, which makes 6 square root of 3, okay? 3 square root of 3 plus 3 square root of 3 makes 6 square root of 3. Okay, well now I have enough information to figure out what the area is going to be. Our area is equal to 1/2 A times P. Well, we found our apothem is 3. Okay, that's the height of the triangle. So we have A is equal to 1/2 times 3. And the perimeter, well, the perimeter of our triangle is just one of the side lengths times the number of sides. Well, a triangle has 3 sides, and my side length is 6 square root of 3. So 6 square root of 3 times 3, that's going to give me the perimeter, is 18 square root of 3. So the perimeter of my triangle is 18 square root of 3. Then our calculator, we can multiply things out. We have 1 over 2 times 3 times 18, and we're going to leave it in exact form. So we're going to get the area is 27 square root of 3 centimeters squared. Okay, so we have the area is 27 square root of 3 centimeters squared. Then they also give us an example with a hexagon. And they say the regular hexagon has a side, so not a radius, not an apothem, a side of 8 centimeters, okay? So what they're saying is this whole length is 8, which means half of the length of this triangle would be 4, and this side would be 4, okay? Well, the reason that's useful, again, we have a 30, 60, 90 triangle, okay? So in this orientation of 30, 60, 90, remember this is our short side, our long side, and our hypotenuse. Well, they say since the side length is 8 and this side is 4, then this side is double 4, which makes this 8, so the radius would be 8. And then our apothem, the height here, would be 4 square root of 3. Okay, so our apothem would be 4 square root of 3. Well, now I have enough information to figure out what the area of this hexagon is going to be. It's A equals 1/2 times the apothem, which is 4 square root of 3. That's what we just found, the height of that triangle, times the perimeter. Well, how am I going to get the perimeter of the hexagon? Well, it's the side length, which is 8, times the number of sides, which in this case would be 6. Okay, so that gives me 48. So the perimeter is 48. Okay, so then we can find our area. It's 1/2. Whoops, let's just go back here and let's do this in our calculator real quick. That way you guys can see. So we have 1/2 times 4 times 48, and then we're going to keep it exact. So we get 96 square root of 3 centimeters squared. Okay, and let's look at one example with a square here. Okay, so it says we have a square with an apothem of 6. So this one's nice to us. They tell us that this is 6. But remember, with a square, this is a 45, 45, 90. Okay, so if that's the case, the two base angles are opposite the sides that are congruent in length, which means this side would be 6, and this would be 6 square root of 2. Okay, so if that's the case, this side would also be 6, which means the length of the entire side of the square is 12. Well, now I have enough information to find the area. So it'd be A is equal to 1/2, okay? Which, of course, if we really wanted to, we know that square is base times height, but just for the purposes, or we could say side squared, but just for the purposes of what we've been working with, I'm going to use 1/2 times A times P. Okay, so we have A is equal to 1/2. Our A is 6, and our P, well, the perimeter, 12 times 4, we would have 48. And then we can multiply that all together. We'd have 1/2 times 6 times 8, which gives us, 48. Go back there. There we go, 144. So we get 144 centimeters squared. Okay, 144 centimeters squared. Now, again, since it's a square, we could actually just say it's side squared, or if you want to think of it as base times the height, this would still be 12. 12 times 12 gives us 144. But we still get to the same result. Okay?